Picture a hunter cruising through open water for hours, senses sharp, and still gliding straight past a body floating close enough to touch. That's not bad luck. The prey pulled off something stranger than hiding. It let the ocean pass straight through it instead of blocking the view. Welcome to the world of transparent animals, where invisibility isn't a disguise painted on, it's a body built to get out of light's way entirely. Camouflage usually means matching a background, sand, coral, shadow, but transparency skips all of that by refusing to depend on any background at all. A see-through body works in darkness, in sunlight, against rock or open blue, which is exactly why this trick shows up again and again across the animal kingdom. Jellyfish drift this way, so do squid, worms, shrimp, baby fish, even a few frogs and butterflies. Completely unrelated animals landing on the same solution. But here's the catch nobody expects. Turning invisible is far harder than simply losing your color. You can strip every pigment from a body, and it will still be perfectly visible, because color was never the real problem. Light gives objects away through absorption, reflection, and scattering. 3 separate ways for a shape to announce itself, and pigment only controls the first one. Every place inside a body where one material meets another, skin against fluid, fluid against muscle, muscle wrapped around nerve, bends light slightly off course. That's the same reason a pane of glass turns visible the moment it's cracked or dusted with scratches, even though the glass itself never stopped being clear. An animal is that cracked pane taken to an extreme, packed with membranes, fibers, blood cells, and organs, all shoving light in different directions at once. So true transparency means silencing hundreds of tiny reflections at once, not just draining out the color. Ocean life gets a head start here because animal tissue is already mostly water, and water meeting water barely bends light at all. The closer two materials match in how they bend light, the less that boundary reflects, and the less there is for an eye to catch. That single fact explains why transparency crowds the open ocean, especially far from any reef, rock, or plant to hide behind instead. Down there, in 3 dimensions with no floor and no ceiling, an attack can come from above, below, or either side without warning. Color patterns need a predictable backdrop, but a body drifting in open water might hang against black depths 1 second and blazing sunlight the next. Transparency doesn't solve either lighting condition perfectly, but it survives both, bending with whatever brightness happens to sit behind it. Jellyfish take this furthest of all, since a bell is almost entirely water held inside a thin film of living cells that barely touch the light passing through. Comb jellies work the same way, though the rows of hair-like cilia they beat to swim can split sunlight into flashes of rainbow color, betraying them for an instant. Salps push transparency into stranger territory, barrel-shaped drifters, distant relatives of vertebrates that pump water straight through hollow bodies to feed and move at once. Their disguise nearly works, right up until a darker gut, a clump of reproductive tissue, or the faint seam where body meets water gives the shape away. And that's the real problem hiding underneath all this. Some organs simply cannot do their job without interacting with light, no matter how clear everything around them becomes. A stomach takes on the color of whatever was just eaten, and there's no way to make a digestive tract optically empty on command. Blood can sketch out the entire branching map of circulation, while muscle and connective tissue turn cloudy wherever proteins pack in tightly enough to scatter light. Add shells, bones, or armor, and the problem compounds, since the strongest building materials in nature usually bend light, nothing like the water around them. Transparency, then, favors bodies that stay thin, soft, and watery, though evolution keeps finding ways to sneak past even those limits. Plenty of drifting crustaceans have gone nearly clear already, reduced to shells you can see through, with only eyes, gut, and reproductive organs floating inside like exposed machinery. Even a clear shell throws back enough light to be spotted, so some species have evolved microscopic surface textures that work like tiny anti-reflective coatings. Instead of one strong reflection bouncing straight back at a predator, that surface breaks the light into dozens of weaker scattered glints, each easier to miss. Nobody needs perfect invisibility to survive. A slightly dimmer outline is often enough to make a hunting predator lock onto someone else instead. Multiply that tiny advantage across thousands of generations, and you get bodies that look almost supernatural, built from nothing but ordinary physics repeated over and over. Glass squid push the idea about as far as an animal with a brain, eyes, and full nervous system can push it. Their tissue turns essentially transparent, yet the organs packed inside it remain stubbornly, unavoidably visible no matter how clear the flesh around them gets. Some squid compress their gut into a narrow core to shrink the dark silhouette a predator would see from directly below. Others lean on reflective or glowing structures to paper over exactly the spots that transparency alone could never erase. Posture matters just as much as anatomy here, since rotating the body changes how much tissue light has to cross to reach an outside observer. A squid can look almost absent from one angle and completely obvious from another. A good reminder that transparency isn't a fixed trait, it's a relationship between body, light, and where you happen to be standing. Some transparent animals go further still, switching on pigment cells the moment conditions change, trading invisibility for ordinary camouflage when it suits the surroundings better. That flexibility matters because a clear body isn't equally hidden everywhere. Brighter water near the surface can throw reflections off tissue that stayed invisible in the dim water below. There's also a threat transparency can't touch at all. Many ocean predators can detect polarized light, and transparent tissue scrambles that polarization even when it barely changes ordinary brightness. So an animal can look completely invisible to a human diver while standing out sharply to the very predator hunting it. Camouflage was never designed with our eyes in mind. It evolved against whatever visual system the local predators actually carry. No structure exposes that conflict harder than the eye, because an eye that let all light pass straight through would be useless for actually seeing anything. A retina works by absorbing photons, which means it has to stay dark, turning the eye into a small, unavoidable shadow inside an otherwise glassy head. Plenty of transparent animals respond by shrinking their eyes, flattening them, angling them differently, or wrapping them in reflective tissue that mirrors the light around it. Some deep-sea species take a completely different route, aiming rows of light-producing organs downward to erase the shadow their own bodies cast from below. Scientists call this counter-illumination, and it doesn't make anything transparent. It simply replaces a dark silhouette with manufactured light matched to color and intensity. Put those two tricks together. Clear tissue that lets ambient light through, plus glowing patches exactly where a shadow would otherwise form, and you get one of the ocean's most complete disappearing acts. It's also why transparent animals often look strangely unfinished to us, as if the rest of the body vanished and only the eyes and gut were left stranded behind. Those visible leftovers aren't mistakes evolution failed to fix. They're the price of being able to see, eat, breathe, and stay alive at all. Transparency shows up most often early in life, when a body is still small enough for light to slip through without hitting much pigment or dense tissue. Fish that grow into brilliantly colored adults frequently start out as clear slivers, little more than a pair of eyes and a thin line of organs suspended in water. At that size, staying unseen is worth more than any pattern, since there's no territory to defend and no mate to attract yet. As the animal grows, muscle thickens, bone hardens, organs swell, and the distance light has to travel through the body keeps getting longer. Past a certain size, that original transparency becomes almost impossible to hold onto, and pigment starts earning its keep instead, for camouflage, for signaling, for blocking radiation. The clear larva and the colorful adult aren't contradicting each other, they're just two different answers to two very different sets of dangers at two different points in one life. Baby eels called leptocephali take this to an extreme, flattening into thin, leaf-shaped bodies with almost no muscle and a gelatinous, glass-like core. Drifting near the surface, they look less like animals and more like scraps of living glass, right up until metamorphosis reorganizes them into the dense, familiar shape of an eel. That temporary transparency proves appearance isn't only tied to habitat, it's tied just as tightly to the physical demands of a particular stage of growth. A tiny drifting larva can afford a fragile, watery body that would be completely useless to an adult fighting currents or forcing its way into tight spaces. Even in the ocean, where the physics favor transparency more than anywhere else on Earth, invisibility still has to be traded off against strength, speed, and everything else survival demands. Step onto land, and that whole balance flips, because living tissue is nothing like air optically. Every patch of skin becomes a sharp, reflective boundary. Land animals also need thick barriers against drying out, solid skeletons to fight gravity, and pigments to block sunlight, and every one of those requirements works against transparency. Build a jellyfish-style body at land scale and it wouldn't stay hidden for long. It would collapse under its own weight, dry out, and burn before camouflage ever mattered. That's why land animals mostly restrict transparency to thin structures, the places where light simply doesn't have much material left to cross. Insect wings are the obvious example, a membrane so thin it's basically two layers of cuticle stretched over a scaffold of narrow veins. Strip the colored scales off that membrane and it turns clear, though the bare surface underneath can still shine like a tiny window catching the sun. Glasswing butterflies cut down that reflection with sparse scales and microscopic surface ridges that let light pass through instead of bouncing straight back at an observer. Their wings still catch the light at certain angles, especially in rain, but against shifting forest shade they're genuinely hard to track. The body and wing edges stay colored too, so nothing about the butterfly vanishes completely. The trick is breaking up a familiar outline, not erasing it. Camouflage rarely needs to achieve full invisibility. Buying a predator half a second of confusion is often all it takes to get away. Glass frogs take a completely different approach, using translucent skin and tissue on their underside to blend into the green light filtering down through a leaf. Their backs stay solidly colored, but the internal outlines underneath soften just enough to blur the sharp line between frog and plant. During the day, while resting in plain sight, several species pull off something stranger still. They pump most of their red blood cells out of circulation entirely. A 2022 study led by researcher Jesse Delia found the frogs pack those cells tightly into the liver, tucking away the one tissue that's almost impossible to make transparent. That's a strange move biologically, since red blood cells only work because they're packed with strongly colored hemoglobin built to carry oxygen. Pulling them out of circulation improves the disguise, but it also creates a real problem. Blood that concentrated should clot almost immediately. Somehow the frogs tolerate it anyway, then release the cells back the moment they need to move, and researchers still don't fully understand how they dodge the danger. This is where transparency stops being a fixed property of tissue and becomes something the animal actively manages, shuffling material around its own body depending on whether it's resting or active. The frog isn't hollowing itself out, it's just hiding one of its most visible parts inside an organ that was already easy to overlook. And that distinction matters. Being colorless and being transparent aren't the same thing, since clear plasma lets light through while red blood cells absorb it strongly. In most animals with backbones, blood alone would block real transparency even if every other tissue cooperated perfectly. Antarctic ice fish remove that obstacle for a completely unrelated reason. Several species simply lack working hemoglobin, leaving their blood pale and nearly colorless. Their bodies can look strikingly see-through, but that trait evolved for surviving cold, oxygen-rich water, not for hiding from anything. Cold water holds far more dissolved oxygen than warm water, and these fish have circulatory adaptations that let them get by with barely any hemoglobin at all. They're a useful warning here. Two animals can look almost identical and see-through, yet arrive there through completely different evolutionary paths for completely different reasons. An animal might turn transparent to dodge predators, because its tissue is naturally thin, because its blood lost its pigment, or simply because color never paid off at its size. Often more than one of those reasons applies at once, which makes it genuinely hard to hand any single transparent species one tidy explanation. Whatever the cause, losing pigment costs more than looks, since pigment often does jobs that have nothing to do with camouflage, blocking UV radiation, protecting fragile molecules from sunlight damage. Strip that protection away, and an animal may need to avoid strong sunlight, repair damage faster, or hold on to whatever protective compounds it can still afford. Clear tissue also has a side effect nobody asked for. It can expose parasites, injuries, developing eggs, or a recent meal to anyone paying attention. Even a transparent predator pays that price, invisible while stalking prey, yet just as exposed the moment something checks whether it's eaten recently or where its weak points sit. Some species patch those weak spots with reflective coverings, tightly packed organs, or small patches of pigment placed only exactly where concealment matters most. So evolution rarely builds one uniformly clear body. It usually builds a patchwork of transparency, reflection, pigment, and glow, stitched together piece by piece. Every piece answers a different source of visibility, the same way a genuinely quiet engine has to kill vibration, friction, and airflow noise separately rather than muting one and calling it done. Skin decides how light meets the body first. Internal tissue decides how much gets scattered afterward. Organs cast the shadows nothing can remove, and behavior decides which angles a predator ever gets to see. Even the water itself plays a role, since suspended particles, depth, and sunlight all decide whether a tiny imperfection becomes noticeable or disappears into the noise. Near the surface, strong light can expose reflections that deeper water would have hidden. But deeper water makes whatever silhouette remains stand out sharply against the faint glow from above. Past the point where sunlight runs out completely, transparency mostly stops paying off, unless an animal is trying to dodge the bioluminescent flashes produced by other creatures nearby. Plenty of species actually change strategy with depth, age, or time of day, leaning on transparency wherever background light exists and switching to darker camouflage once the water turns black. That's exactly why no single transparent body dominates the ocean, despite how close to perfect the whole idea sounds on paper. Every habitat sets up its own optical puzzle, and every lineage walks in already carrying its own organs, materials, predators, and evolutionary baggage. Evolution never gets to start from a clean sheet of glass. It has to modify an animal that already needs to eat, breathe, move, and reproduce along the way. That constraint is exactly why the same trick keeps reappearing in unrelated lineages so impressive, since none of them arrived at transparency by copying the others. Jellyfish simplified their whole body plan, crustaceans polished their surfaces, squid paired clear flesh with glowing organs, insects thinned their wings down to almost nothing, and frogs learned to rearrange their own blood. None of them reached true invisibility, yet each one stripped away enough visual information to make recognition slower and survival just a little more likely. Predators keep answering back too, sharpening their vision, tuning into polarized light, or learning to hunt straight for the eyes and gut that transparency can never fully hide. And prey keep responding in turn, which means this whole contest isn't fought with armor or raw speed, it's fought over the management of individual photons. Seen that way, transparency isn't really the absence of a feature at all. It's the product of constant adjustment happening at every scale, from whole organs down to structures smaller than a single wavelength of light. It takes chemistry that avoids absorbing light, anatomy that limits scattering, surfaces built to suppress reflection, and behavior that keeps the body angled toward the most forgiving light available. Let just one of those layers fail, and the whole animal snaps back into view. A single dark eye is sometimes all it takes to expose an otherwise perfect glass squid. That fragility is probably why transparent animals read as so delicate to us, balanced right on the edge between staying hidden and staying alive. They can't erase every internal boundary completely, because life itself runs on boundaries, membranes separating cells, organs splitting up jobs, tissues holding the gradients that keep metabolism running at all. Total optical uniformity would mean dissolving most of the organization that makes an animal in the first place. So transparency runs up against a hard biological ceiling, letting a creature blend into its surroundings without ever fully dissolving the structure that keeps it functioning. The closer any species pushes toward true invisibility, the more carefully it has to hide the stubborn evidence that it's alive at all. Blood still carrying oxygen, eyes still capturing light, a gut still holding whatever it last ate. Those leftover traces are exactly what make transparent animals so strange to watch, because you can see the whole conflict between hiding and staying alive playing out directly on their bodies. A jellyfish drifting through blue water looks almost absent, right up until a faint contraction gives away the living machine quietly holding itself together underneath. A glass frog asleep on a leaf looks pale and still, while deep inside, its blood sits packed away in hiding until movement forces it back out. A squid rotates in the sunlight, and for one single angle, its whole body disappears while the dark geometry of its eyes stays suspended in the water regardless. Every one of these animals disappears in its own specific way, because transparency was never one invention. It's a negotiation between light and living tissue that keeps getting solved from scratch. The open ocean offers the closest thing to ideal conditions for that negotiation to actually succeed, which is why its waters are full of creatures that look less like solid animals and more like temporary disturbances in the water itself. On land, only wings, thin skin, and small patches of tissue usually get anywhere close, held back by gravity, dry air, sunlight, and the sheer optical gap between living tissue and empty air. But across both worlds, the goal was never to become literally nothing. It was always just to erase enough evidence that the next pair of eyes makes one fatal mistake. What looks like ghostly beauty to us is really a brutally practical solution, built out of rerouted blood, watery tissue, microscopic surface textures, narrowed organs, and carefully placed light. Transparency never makes life simpler. Every invisible surface hides a complicated, ongoing solution to the problem of staying functional while barely being seen at all. The nearly invisible animal drifting in front of a predator right now is still solid, still hungry, still vulnerable, still completely alive. It's just that, for one crucial moment, the light passing over it carries almost none of that story away.